So let's have a look at some of our programs. Or first of all, let's give you an overview about where we fit into the university. University of Adelaide, you're here today, so you've seen how beautiful the campus is. You've seen how well the campus is located in the heart of the city. The transport to this campus is second to none. You've got train networks coming in from everywhere, bus networks coming in from everywhere. I live down in Hallett Cove. I certainly find this the easiest campus to get to. The other thing is, once you're here, it's a great student lifestyle. You're right in the heart of the city. We've got lots of resources here on campus, but if you get fed up with those, you can always wander into Rundle Mall, Rundle Street, loads of cafes to go and have a coffee and just sort of chill out a little bit when you need to. So very, very nicely located campus. The University of Adelaide is a very successful university. We're ranked, I think, in the top 1% of the world's universities. So it's not a bad university to consider coming along and joining. So I'm going to talk about that. I have spoken about that already. I'm also going to talk about the fundamental role of engineering, computer science and mathematics. I'm going to look at some of the industry requirements, i.e. what industry expects our graduates to have once they finish here, what career prospects there are for you once you graduate, some examples of our more famous past graduates, and towards the end I should have a bit of time left for some questions and answers. So I was ahead of myself. I was already starting to talk about how fabulous the university is. That second line down looks a little bit cliched. We produce world-ready graduates, not just job-ready graduates. Sounds a little bit cliched, but it is true. As you'll see, a number of our programs are actually accredited, and that accreditation gives us recognition, or gives your programs recognition in other countries as well. So as a graduate from our university, a number of those programs are recognised across the world. So you can hit the ground running in a number of countries where your qualifications are actually recognised as well. The other thing that you'll notice about, if you used to start digging deep into the leaders of local industry, leaders in politics indeed as well, you'll see that many of those leaders, whether they're industry, politics or wherever, all walks of life across South Australia and Australia, you'll see that many of those leaders are actually graduates from our university. So our graduates do actually make a difference. They go out and they're certainly amongst the leaders of the state and the nation. One of our most famous ones, Julia Gillard's. Now, I know a lot of people don't like Julia Gillard, so whether you do or whether you don't, she didn't actually finish here, okay? So if you like her, she was one of our students, but if you don't like her, she didn't actually finish here. She finished somewhere else, so there we go. Why be an engineer, mathematician, or computer science? To make a difference. You do make fundamental differences. You make huge differences. James Kit Finch, American engineer and educator. Engineers make history. Put your hand up if you recognise what that picture's from. I'm going to pick on you. Here's one. Yeah, where's it from?
The London Olympics.
It is. It was the opening ceremony of the London Olympics. What was it portraying? I can hear murmurs saying the Industrial Revolution. Absolutely right. The Industrial Revolution, a period that occurred between around about 1750 to 1850. It was a monumental part of history. It changed the world. Engineers rose above what seemed at the time to be insurmountable problems. They laid railway tracks across the UK, across Europe, and they opened up transport right across the world. Built ships that had never been the size that had never been conceived before. And by opening up these transportation pathways, industry started to boom. When industry started to boom, new engineering inventions started sort of coming up left, right, and centre. So it changed the face of the planet. Without the Industrial Revolution, well, I don't know where we'd be, but we certainly wouldn't be in the situation we are now. You wouldn't have been coming to here today either by car or by train. Probably not too many people came by ship, but you get the idea. I mean, this was a monumental sort of time of change, and engineers made this happen. Australia came, where did they come in the Olympics, by the way? 10. Anyone know where England came in the third? Let's have a look at some of the other changes that have happened over the years as well. I was born in the 60s. I wasn't actually practicing a practicing engineer in the 60s, but in the 80s I was. And I remember when I was working on some missiles, and I had to do a bit of analysis on these missiles. And the size of the computer then, it was what we call 2 6-foot racks. So if you imagine 2 racks, 6 foot tall, chock-a-block full of electronics and resistors and transistors and all these sort of things, and this horrible green on black computer screen that took ages to do any sort of calculation. And that was, if you like, the forefront of technology at the time. It was British Aerospace Dynamics, a very sort of a rich research and development company. Okay, so money wasn't too much of an issue for them. But nowadays, more computing power is found on these things. Not just these things, but the iPhone that I generally carry in my pocket, not today, just in case it goes off. It keeps going off when I'm doing lectures. More computing power than the computers that I was working on in the 1980s. So this advancement of technology is made possible not just by engineers, but by computer scientists and mathematicians that underpin the very fabric of engineering and computer science. Okay, so the technological advancements that we've been seeing and continue to see, all the result of engineers, computer science and mathematicians all working together. So, bit of a slide there, just explaining, I suppose, the difference between comp sci and mathematics. Mathematics, the study of quantities, numbers, obviously, manipulating numbers, having fun with numbers as well. Comp science, creating software solution to real-world problems. Everything that we do in our lives, and I know I'm probably sort of banging the drum a little bit here, but you know, I don't feel I can emphasise it enough. Everything that we do in our day-to-day lives is affected by engineers, maths, and computer scientists. There we go. There's a pen, a little pen. How many bits have got in it? 1, 2, 4 components. Each one of those components, you think about what's gone on just to make that little cap. There would have been a lot of tooling that goes into that. The tooling would need to be designed for that plastic to be injection moulded. Somebody would have had to work out all the flow properties of the plastic when it goes in there, whether it's going to be strong enough, whether that pen's going to be strong enough, make sure it's not dangerous to the consumer. So even something as simple as a pen that you can just pick up from a desk, huge amount of engineering that's gone into it. That's one end of the spectrum. Other end of the spectrum, you see engineers, comp science, mathematicians working for NASA, working on the space projects for NASA. So very, very sort of wide, diverse range of jobs, I suppose, and responsibilities that engineers, mathematicians, and comp scientists can actually have. When you wake up in the morning, or as you woke up this morning, I'd imagine most of you probably had a shower. But as you turn on that shower, it's not just the design of the shower head and the fact the shower head was manufactured, but the way that the water actually got to that shower head, the infrastructure of the pipelines that went down, the fact that water's not poisonous, the fact it's been chemically treated just to the right level so it's not poisonous. I mean, you don't want to get rid of all the germs only to be poisoned by all the chemicals they put in there as well. All of this is engineering. All of this is worked out by engineers and mathematicians and comp science. Computer scientists, all working together collaboratively in teams towards all of these sort of products and services that we just take for granted. So, some fundamental roles here of engineers, maths and computer science. Extracting natural resources, mining. So obviously a very heavy involvement in the mining industry, petrochemical industry and gas industries, and actually turning those resources into usable products, but also doing it in a very responsible way. Sustainability, it's a word that we hear more so these days because we recognise that these resources are not an infinite supply, they're a finite supply. So a very crucial part of engineering is to use these resources very responsibly and consider the whole life cycle of what we design. The greatest challenges of the 21st century as identified by the National Academy of Engineering. Here's a list, a bit of a shopping list of some of the things, the main sort of challenges. Make solar energy more economical. Okay, solar energy exists, but is it running, or are we using it its most efficient? Make it more economical. It's a challenge. Provide energy from fusion. Develop carbon sequestration. Let's jump over there. Secure cyberspace. Prevent nuclear terror. reverse engineer the brain. All of these are huge, big challenges that face us as people, as the general populace of the world. These are major challenges that still affect us. Let's have a look at who's looking at solving these challenges at the moment. Mechanical engineers. Actually, I jumped right to the end of that there, but mechanical engineers, comp scientists, mathematicians, all these people are working on these issues, improving these issues, and undoubtedly, in years to come, will have solved what at the moment seem to be almost impossible solutions to problems to solve. The good thing about going into any of these vocations, whether you want to be a mathematician, a pure mathematician, whether you want to get into software design, computer science, engineering, civil engineering, mechanical engineering, whatever, there's a national skills shortage. And the good thing about that is that when there's a national skills shortage, it places you guys in demand. That means you get choice of who you can go and work for, and also it pushes the salary up as well. So it can be a very lucrative area. Any of these can be a very lucrative area to work in. Towards those skill shortages, you can see that as a faculty, we've got a lot of programs up there. Okay, all of the schools and the faculty have a number of programs. In actual fact, there's more than that. Some of those programs have what are called double degree programs. And I'm not going to name them because I got into trouble this morning for naming the wrong ones. But if you look at the literature that you've got in your goodie bag, you'll see that there are a number of double degree programs. And what that means is we've tried to save you a bit of time. We thought, okay, let's look at degree A and look at degree B. Let's look at where there's a bit of repetition, get rid of that repetition and squish up the time frame. And we've managed to do that on a number of programs and bring 2 degrees down into a 5-6 year period, okay? So we actually sort of squished those down. They're very specific programs. Of course, you can go and enroll in as many degree programs as you like and do those simultaneously, but it will take you a long time. We've picked a few, married them up, and we squished them down to 5 years for you. Right, a couple of new programs just to add on there. We've got a Bachelor of Computer Science, Bachelor of Mathematical Science Advanced. These two programs are really aimed for people that are going to have a high TER. These are going to be a little bit, what's the word? I was going to use the word elite there, but I suppose it's got the wrong connotation. But for people who have got an ATAR, anticipating an ATAR 95 and above, this is the intent for these two new programs being introduced. Just looking at a few specific areas. I'm conscious this morning I missed out on a slide about prerequisites. Is that to come? Okay, I haven't got there yet, so I haven't missed it yet. That's okay, good. So I'll keep going. Let's look at some of the areas, some of the more specific areas. Mining engineering. Mining engineers, it's certainly one area you can get into. Obviously, you're looking at mining, but there's a whole lot of other stuff that's not quite so obvious. Okay, I want to work in the mines. I have to be a mining engineer. Not true. Not true. Obviously, there are jobs for mining engineers in mining, but think about the infrastructure that goes in place. Think about the roads that need to be built for these mines that are in the middle of nowhere, the fact that power lines need to be laid on, vehicles need to be designed and effectively operated, huge mining trucks. What's going to get these minerals out of the ground? All the equipment that needs to go into it. Some of these vehicles, they might be automated. A lot of the big Caterpillar trucks can automatically sort of drive themselves. I don't know whether they do. I think they still have a driver in there, but they can basically be guided and controlled by navigation, GPS. That demands computer scientists, computer engineers to go in and simulate all of this stuff. So the whole mining area, there's an immense amount of opportunities, not just for mining engineers, but all sorts of engineers, all sorts of mathematicians and comp science. If you want to look more specifically, though, just at what mathematicians do, what comp science graduates do, mathematical models of ore bodies, estimation of reserves and resources, optimizations of produce, comp sciences, computer-aided mine design, virtual reality simulator. Actually, I'll just pick up on that one there. I mentioned that you've got these huge trucks that can follow sort of GPS signals and be automatically controlled around the mines. If somebody came up with that, they wouldn't sort of think, yeah, I think I've got it about right, let's give it a go, see what happens. They wouldn't put this technology straight out to these huge monster-sized trucks. They'd simulate it first. They'd run computer simulations to make sure it was safe and effective when they tested it and when they simulate it, then they push that technology out into the real world. So computer simulations, virtual reality simulations, certainly something that our graduates end up getting into. Opportunities for graduates in the mining, continuing on. Engineers, again, the obvious one, mining engineers, where you're basically getting straight into the nitty-gritty of mining. Again, I've really sort of covered this already. I've stolen my thunder on this one. But infrastructure and the like, that all supports the mines as well. Good thing about the mining boom, by the way, is that's been like a black hole to an extent, and it's sucked in a lot of graduates from all over the place, which has created broader openings for all of our graduates in other areas besides mining. Electrical, electronic engineers, well, basically anything that's electric is going to call for electric and electronic engineering, whether it's something that's battery powered or whether it's something that you're going to plug into a hole in the wall. So there's not too many things that we use nowadays that are not that don't have electronic. Who, for example, hasn't got a mobile phone in their pocket? There's a couple of you, but you probably left it at home because you wanted the day off of your boyfriend or your girlfriend ringing you, yeah? But, okay, so most people nowadays have an electronic device in their pocket that they carry around with them everywhere. So, where are we going? Software engineering. Software engineering, surprisingly, software engineers design software. Artificial intelligence, computer graphics. When I walk around Innova building, so it's not called Innova building, the Ngani Wardley building, it's Innova was its project name. There's a lot of TV screens around the various levels, and some of the computer graphics that these guys produce is absolutely incredible. Pharmaceutical engineering, well, you're not learning to be a pharmacist, but what you're doing, you're enabling pharmacists. Okay? You're looking at everything from drug discovery or the equipment and the processes that assist drug discovery through to drug delivery, and that might involve methods of perhaps combining or separating sort of chemical compounds, machinery to do that, right through to the packaging that these drugs end up in. I mean, if you look at this silver foil package, something's got to punch those out, something's got to put the drugs in there and put them in the little boxes. And this will be ingenious sort of little device, well, not little devices, but big sort of mechanised devices that automate all of this. Petroleum engineering, again, a lot of opportunities there for petroleum engineers, a lot of offshore work, a lot of on-land work, but also not only that, a lot of corporate type work. Engineers can follow two different pathways. You can end up following a pathway of technical expertise, or you can follow a pathway of project management and people management. So even if you end up being a petroleum engineer, you could be out on the oil rigs, the excitement of the oil rigs, or you could be managing projects from the heart of the CBD. The Westpac building used to be called the Santos building, so it gives you an idea how many employers Santos would have had in the heart of the CBD, many of whom would have been engineers. Still are engineers. Actually, a lot of my graduates end up working for Santos. Mechanical and sports engineering, this is a program that's sort of very en vogue at the moment. The popularity of this is rising quite dramatically. A lot of students see this as an opportunity to marry their sporting interests with a potential profession. Indeed, one of our students, the third-year students, James McRae, was one of the bronze medalists in the men's quadruple sculls. So, that's a student that's very passionate about designing equipment to legally enhance the performance of athletes, whether it be equipment they use during the event or in the build-up to an event, to sort of get their peak power and monitor their performance. So if designing all that sort of stuff, inventing those sort of things interests you, and you want to combine your career with your passion for sports, mechanical and sports engineering is a pretty good program to consider. Sustainable energy engineering. Maybe you've got a passion for designing and improving wind farms, the technology on wind farms or solar panels, or maybe processes to extract biomass or biofuels, biodiesel more effectively. Maybe you want to come up with a process that creates biodiesel without sort of having a problem or creating a problem for all the orangutans and the like. I mean, these are real world problems. And whenever you get into sustainable energy, you can guarantee that initially where you see, hey, this is going to be a solution to all the world's energy problems, a problem's going to pop up as well. So engineers are faced with solving all these sort of issues. A couple of things that our students have done. The BioBike, that was one of our students' projects. That was a biodiesel motorbike. It won the Green Fleet Award in the 2007 World Solar Car Challenge. It's not a car, it's not a solar vehicle, but they had an alternative class for alternative energy vehicles. The bio bike, subsequently got named Betty. Probably didn't need to know that, just thought I'd tell you. Subsequently got renamed Betty. She won that event. She went on, she actually gained a bit of interest from that point forward. There's an author called Paul Carter who picked up on the publicity of that. Anyone know the author Paul Carter? Or heard of the author Paul Carter? There's actually two. There's one that writes stuff about animals. He's a vet. There's another one who used to work on the oil rigs. He wrote a book called Don't Tell Mum I Work on the Rigs. She thinks I'm a piano player in a whorehouse. Yeah? Yeah, well, he wrote that. It's an amazing read, by the way, really, really funny. He blew up his pet monkey with a hand grenade, as you do. But he felt a little bit guilty about some of the stuff that he'd done, the way that he'd sort of extracted all this stuff from the earth. So he wanted to raise a profile on sustainable energy. And he borrowed our motorbike, my student's motorbike, that was designed and built by my students. And he rode it all the way around Australia. And he wrote his third novel, Is That Thing Diesel? So I don't know if anyone's read that. I had to go to my doctor's actually a few months ago, and I saw the book sitting on his shelf there, and because Paul actually mentioned it, and he goes, "Is he talking about you?" And he was looking forward to me getting sick so that I could go in and see him just to talk about the book. So our students do some really great things anyway as well. Hybrid solar car, for example. What else we got here? Oh, career prospects. Okay. The career prospects are huge, absolutely huge, and I was talking about mechanical engineering in my last presentation, and I had 3 slides of career prospects for mechanical engineers. Well, that's just for mechanical engineering. The same sort of opportunities are there for electrical engineers, civil engineers, comp sciences, mathematicians. The opportunities and the prospects for you are actually huge. As I said earlier, there's a skill shortage for all of these areas. You keep hearing people talking about science shortages. I mean, there's not a week goes by when they say we haven't got enough engineers, we haven't got enough science. It's true. It's true. And the good thing about that is, as I say, it creates opportunities for you guys if you graduate with one of these degrees, and it puts you on a good salary. So let's look at the program structure. I mean, if I'm whetting your appetite and you're thinking, yeah, this sounds half decent, what would you be up for? 24 units per year of study. Now, it doesn't mean 24 subjects. Each of our subjects or courses, whatever you want to call them, is worth 3 units. So 3's into 24. I'm really tired, so I'm not going to do the maths. That's how many subjects you have to study a year. Generally, there are 4-year programs. The engineering programs are 4-year programs, although the programs in comp sci are 3 years. So you're up for 4 years for engineering, comp sci, 3 years. In comp sci, honours is an extra year. So if you want to do an honours degree in computer science, you've got to do an extra year, bring it up to 4 years. In engineering, honours is not an additional year, it's an award level. So if you get a good enough grade, you'll end up with an honours. If you don't quite make the honours mark, you end up with an ordinary degree, a Bachelor of Engineering. How am I going for time? All right, am I? Good, thank you. All right, so again, you think, that all sounds pretty cool, I can handle all that. What I have to do at school, what I have to do to put me on the right pathway to enrolling here. And there's your answers. Maths studies, certainly. Specialist maths, huge bonus. Physics with assumed knowledge of chemistry. Oh, chemistry is a prerequisite for
chemical engineering from 2014.
Okay, so chemical engineering becomes a prerequisite rather than just assumed knowledge for chemical petroleum engineering. If you do specialist maths, you can go straight in and do the single degrees. If you've only done maths studies, the best pathway is the double degrees, where you...
There's a few different options, and if you're worried that the prerequisites are not quite right, please come and speak to us. We'll speak to you about your individual situation and what might be the best pathway option for you. But if you're thinking engineering, we recommend maths studies, specialist maths and physics to keep your options the most open. Certainly think about chemistry if you want to do chemical engineering, and if you can fit chemistry anyway, it's an assumed knowledge for a lot of our degrees as well. So maths and science.
Great. Yeah, I was going to sort of try and say a golden rule there, but there's always a few exceptions to these golden rules, these general rules. So, yeah.
Degree to degree, so I highly recommend you make sure that you familiarise yourself with what the prerequisites are for the degrees that you're interested in. And if you have any concerns or questions, please speak to us in the faculty office, and we're happy to talk you through your scenario.
But if you haven't done specialist maths, if you're not doing specialist maths, there are pathways into engineering. I think it's probably a fair,
There are some
yeah.
options. If you're in year 12 and you haven't done any specialists, speak to us and we can talk you through some options. But if you have the opportunity to undertake specialist maths in year 12, strongly recommend you do it, because the reality is we'll make you do it once you get here anyway.
Yeah.
And if you undertake it in year 12, you're entitled to some bonus points from the University of Adelaide on your ATAR, so it's a really good option if you can fit it into your year 12 study plan.
That's true. That's very true. Let's look at an example. Let's say you do mechanical engineering and you're really passionate about mechanical engineering, but you've just realised that you haven't done specialist maths. You could come in to a program that allows entry for maths studies, in which case you do have to do an additional maths unit when you're in here, a maths course when you're in here. There are a lot of opportunities to transfer between programs once you're through the door as well. So just to bear in mind, I think, I don't want anyone to look at this and say, oh, damn, I can't get in. There are always pathways for solving some of the problems that arise. Here's a nice list to look at. You can see that engineers and mathematicians and even comp sciences are all in the top 8 of the median salaries here. Dentistry is right at the top there. These are median salaries for graduates. Who smokes? No, I don't. Well, I thought there'd be a few more hands going up. But if ever you looked on the cigarette packets now, they show you the state of some people's mouths, and they're really horrible. So who would want to get into dentistry now when you've got to deal with some of those? Really, even with those pictures, those horrible mouths. Oh God, not me. I'd go straight to number 2. I mean, that's the yeah. In actual fact, I think those figures are very conservative. The amount of students that sort of knock on my door and say, hey, Colin, I've got a job. Oh, great, yeah, good on you. And I'll say, what you on? What sort of salary you're earning? They tell me the salary, and I try to stay happy. But when you find out that these graduates are earning more money than you're on yourself, God, I'm nearly 50, it does get a little bit depressing sometimes. So in some cases, and I do stress the point, I don't want to say that you can go out and sort of be a millionaire straight away. In some cases, you can double that. Okay, so there are opportunities where you can actually double that figure. But the median salary is 59.6. So good money to be had out there.
That's a starting.
Sorry?
That's a starting.
That's a starting salary. If you get yourself on a graduate program, you get a graduate programs once you graduate. A graduate program, you get accelerated career paths through the company, and your salary literally just shoots up. Some of our famous graduates, Andy Thomas, he was a graduate at the School of Mechanical Engineering. He liked it there so much he stayed on and did a PhD. When we couldn't really give him any more to sort of keep him interested, he went off and became an astronaut. So he's probably one of our most famous graduates. We've got Didier Elzinger there from Maths and Comp Sciences. He's done all the cool graphics and the CGI stuff. We're responsible for all of that for films like The Lord of Rings, just to name but a few. Aurelia Helfgott, a senior research fellow at University of Oxford. A lot of our graduates actually end up becoming Rhodes Scholars and getting pathways into Oxford or Cambridge. Alan Noble, Bachelor of Electronic Engineering, the Engineering Director for Google Australia and New Zealand. So again, just a few examples there of some of our very successful, very highly publicised graduates. As I said earlier, you haven't got to dig too deep below the surface to find out that a lot of our nation's leaders, industry leaders and politicians are actually graduates from the university here. So I think I've covered everything there, and nothing I've sort of skipped that I need to go back on. So got time to answer a few questions? Oh, I have. I've got the nod. I can answer a few questions. Yes?
Going back to the prerequisites.
Yes.
Is it maths studies and specialist maths, or specialist maths as a preference?
It depends on the degree, but most of our degrees that require the specialist maths will also require maths studies. So pretty much every one of our degrees across the faculty would require maths studies, and many of them require specialist maths as well as a prerequisite. For those that don't require specialist maths as a prerequisite, we will need to make up that maths with a maths course that we'll have in your program of study here. So, yeah.
Any other questions? Yeah, you then, you, yeah.
Does engineering software also have computer graphics as a elective? Or is that only for computer science?
I don't know, I'm going to not know that one completely as well. There probably are some computer graphic type courses in there, but if you want to come and have a chat with me afterwards, we can have a look at the course program together. I don't know it off the top of my head, but we can have a chat with some of the staff from that school as well and have a look at whether that course is what you're looking for.
There's a lot of comprehensive information on the web as well. So if you jump on and look up that program, before long you can start digging deep into that program and find what courses there are. And again, you can dig into those courses and find out what the syllabus is in those courses. So a little bit of research on the web, and you can say, if you can't find the answers, then certainly drop us a line and get in touch with us. Yep. Can we have some examples? Now, I've got to be frank with you. I'm a mechanical engineer, so that's where all my sort of knowledge sort of lies. But I would say that any engineering team, well, not any engineering, but a lot of engineering teams would need mathematicians as part of those teams. Maths is integral to engineering, and so there's certainly a place for mathematicians on those teams. More specifically, areas that are I suppose more maths focused. There's a lot of research opportunities, a lot of working for the likes of DSTO, CSIRO, and the like.
A lot of our mathematicians, graduates have also gone on to work, say, in government.
Yeah.
The Bureau of Statistics, Bureau of Meteorology. There's a huge range. I mean, mathematics truly is a universal language that underpins everything. So mathematicians can take their career in a very, very wide range of fields in what their interest might be. But if you want to come and send me afterwards as well, I'll see if I can find, we have a booklet that our School of Mathematics has been giving out called Maths Ads, and it's got a whole range of job ads for people with mathematics qualifications. You'll be able to see the huge diversity that mathematicians can take their career to.
Yeah, and so with the job salary, with the starting for mathematicians, is that in like basically as many jobs as they can?
That's a huge amount of jobs, and that's just, if you like, the medium amount. So
that's an average across mathematical graduates across the country. So that would be people who've gone into a variety of jobs, the huge range of jobs. So some might be more for some jobs, and some might be less. It's an average.
Another area, I was fortunate enough to spend a little bit of time at Cambridge University, and one of the things that was apparent to me was a bit of an obscure area that some of the graduates in engineering and maths went into. If ever you bet on the horses, there's always someone who's been studying the form of horses and think, okay, this one's a sure bet, put all your money on that one in the 230 at Doncaster or whatever. Well, in a similar vein, people are always trying to predict how the stocks and shares markets are going. And the city, well, they're basically working in the city in London, as they call it, is there's a lot of mathematicians that are employed to try and predict how the market is actually going to perform, so that people can make money on the stocks and shares. So again, there's a lot of and engineers. You think at Cambridge engineers would want to go straight into engineering, but they're looking for a career in the city because a lot of the mathematical equations and the formulas and the simulations that engineers use do actually have relevance to some of these algorithms that they run in the city as well. So on stocks and share prediction. So wherever there's numbers, and particularly where those numbers marry up to money, there'll be a lot of money to be made. Okay. Any other questions there? One more, yeah.
How many people do you usually accept for each degree?
How many people for each degree? Well, I can give you a couple of examples for degrees. It's done by school more than programs fundamentally. In the School of Mechanical Engineering, we've nearly got 300 students. I think the other school that's probably up there with similar numbers would be Civil Environmental. Civil Environmental is a similar amount of numbers. Yeah, I'd be guessing on all the other schools, but don't worry about the number of places. If you look at the ATAR rankings, that's really, I think, where to sort of set your sights on. Just study well, get above that ATAR ranking, and you should be good.
Yeah. Apply for the degree that you're passionate about. Don't worry about the numbers, and use all 6 preferences to make sure you've got some backups and some alternates. But yeah, just go for what it is that you want, and make sure you've got a few backups just in case.
That's a very good point there, I think, and you should take a strategic approach to putting your preferences down. As mentioned or sort of implied earlier, there are different pathways of coming in to do the program that you want to do. So if you've got a particular passion, you know, one of these programs is really exciting you and you want to go for it, put that down as your number one preference. Look at some of the other programs that have similar courses, put them down as second, third and fourth preferences. These courses, of course, having lower ATARs. Get in, study well, and then look at transferring across. I've just been told that my time's up. So I had the board at the back there saying your time's up. So all I wanted to know is thank you very much for showing an interest in the University of Adelaide, and in particular our faculty. So have a safe trip home.